welcome back again to another video. So in this video we are going to talk about the reductive elimination. So if you remember, in our previous video we have talked about the oxidative addition reactions. If you have not watched that video, I will put the link above so you can go back to it and watch it and understand what the oxidative addition reactions means. It's a little bit important, like, because the reductive elimination in this case is much more like oxidative addition, but the complete opposite. So if you can understand oxidative addition completely, then it's pretty much easy to understand the reductive elimination too. So let's move on. So let me take a new slide. Okay, so here we are going to talk about the reductive elimination. First, I'm going to explain this using a simple example. Right? Okay, so let's take a complex like this. So let's take the vanadium, and we have a ligand like this one, and we have two methyl ligands. Okay, so in order to undergo the reductive elimination, we have to heat this up. So mostly as a solvent we use TMSO. So when the reaction happens, what happens is, unlike in the oxidative addition, here two ligands will remove from our complex. So here we have our vanadium with our pH2 ligand, so I'm just represented by L, plus we have this CH3 group connected to each other. So this is our basically the reactions, right? So there are some few important details which you have to have some good idea about. Like, the first thing is, if you remember, in oxidative addition, always the oxidation state is increased by 2, but in this case oxidation state of our metal center, right? We are talking about the metal center, reduced by 2. And when it comes to the coordination number, if you remember, in oxidative addition, it's increased by 2. But in this case, you can see two ligands are removing, right? Two ligands are removing, so coordination number is decreased by 2. So let me write it. Coordination number reduced by 2, right? So, and the other main thing is, most of the time, the reductive elimination is undergo through a concerted mechanism. So we have talked about this concerted mechanism type on oxidative addition reaction. So you must know, like, how many steps does this mechanism has. If it's a concerted mechanism, you have to know the bond breaking and bond forming happens simultaneously. So this is one step process, one step reaction, right? This is going to be one step reaction. And the other main thing is, if the reaction mechanism is concerted type, right? If the reaction mechanism is concerted type, the bond forming over here, right? The bond forming over here is mostly non-polar. So in that case, there are three possible reductive elimination processes. So let me draw it up. So first, let's talk our metal center as Mn plus. So there can be like hydrogen and hydrogen over here. So when the reductive elimination proceed, we have Mn plus hydrogen bonded together. This is our first case, and again we can have Mn plus with hydrogen with an R group, plus hydrogen and R group, and again we can have two R groups. These are the most common structures which we have found in reductive elimination processes. So we have Mn plus, two R groups bonded together, right? So these are the main types. Like, otherwise the main examples which we are going to go with reductive elimination. So you must have that idea, right? These are the main points you need to memorize, or you need to understand about the reductive elimination process. So there is another thing which you have to get some idea about. Like, if we take this complex, like let me do a small change to this complex. So let me take a new slide and let's take a complex like this one. This is CH3, this is CH3, here we have another ligand, here we have another ligand, right? So the thing is, if you remember in oxidative addition, we have talked about that always the product, right, when oxidative addition happening in some occasion, the product is always cis, right? The two ligands which are combining together is always cis when it comes to the considered type, right? When it comes to the considered type. So in this case, when it comes to reductive elimination, this is also a considered type mechanism, but when the ligands are removing from a metal center, it do not have to be always in cis orientation, right? It can be like this. Why? Because these two ligands can reorient it. These can reorient it to cis form like this. But to undergo the reductive elimination, right? To undergo the reductive elimination, it should be at cis position to each other. If it's not at cis position, just like this, then first step is it need to reorient it as in the cis form. Then it can undergo the reductive elimination. So we have L2 plus CH3 and CH3. This is the procedure. So if your question asks like if this ligand, if this complex can undergo reductive elimination, your answer should be yes. This ligand, yes, it can undergo reductive elimination, but before it undergoes the reductive elimination, it should reorient it on its own to form a structure with two methyl groups at cis position, and then it can directly undergo the reductive elimination. So these are the main thing which you need to understand about the reductive elimination. So there are another few things which you need to have some idea about. Like the thing is, when the reductive elimination happens, you need to know that metal center gains electron, right? This is a reduction. So when the ligands are removing from our metal center gains electron density, because this is a reduction, right? In reduction, electron is gained by the particular group. So this is basically the reductive elimination. It's pretty much easy, just the opposite of oxidative addition. So I hope you get the idea. So in next video we are going to talk about the insertion reactions.